Welcome to this lecture series in linear algebra. In this lecture, we will further explore the notion of cyclic degree of a vector, and let us recall some relevant things. So T be an endomorphism on a vector space V, and let V be a vector in the vector space V. We define the cyclic degree of V as the dimension of the cyclic subspace generated by the vector V. And as a cautionary point, this is a terminology which I developed just for my own purpose. This is not standard. Okay. And we saw, as a remark, I mentioned that the cyclic degree of any vector is at most the degree of the minimal polynomial of the endomorphism in question. I did not supply a proof of it explicitly, but the material in the previous lecture should be enough for you to fill in the details immediately. Okay, and lastly, we proved something that we will need. So if Px is an eigenpolynomial of T, and V be a generalized polyeigenvector of T corresponding to the eigenpolynomial P, and let K be the smallest non-negative integer such that this becomes 0. There has to be such a K because V is a generalized polyeigenvector corresponding to the eigenpolynomial P. So let K be the smallest such thing, which makes it 0. Then the cyclic degree of the vector V is K times the degree of the eigenpolynomial. Okay, so we will use this fact. All right, so let's move on. Here is one problem for practice, but this is star marked, and in fact, this is repeated from the previous lecture. We did not use it in the previous lecture, but today we will use it, so I have repeated it here. And yeah, this is very simple. Even though this is star marked, that doesn't mean this is hard. It's just that I'm going to use it in this lecture. Okay, so with that, let us proceed. So the point of this lecture is to prove the optimality, or what do I mean by that? So we just mentioned as a remark, or was mentioned in the previous lecture as a remark, that the cyclic degree of any vector in the vector space cannot be more than the degree of the minimal polynomial of the endomorphism in question. In this lecture, we'll show the existence of a vector which achieves the equality there. So here, we will show that there is a vector V where this becomes an equality. So that's the point of this lecture. And we have a small lemma before we do the proof of the main result. So here is the lemma. Fix an endomorphism on a vector space V and Px be an eigenpolynomial of the endomorphism. Then there is a generalized polyeigenvector V of T corresponding to Px such that the cyclic degree of V is the maximum possible amongst all generalized polyeigenvectors of V. So this inequality is obvious because if you restrict T to the space of all the generalized polyeigenvectors, the minimal polynomial of the restriction is same as this guy. So anything that lives in the space of generalized polyeigenvectors cannot have cyclic degree exceeding the minimal polynomial of the endomorphism after restriction. But we are saying that equality can be achieved, and this is a step towards proving it in the general case, meaning where we do not have this constraint that V is a generalized polyeigenvector or anything. So anyway, this statement is simple to understand and also easy to prove, so let's prove it. So we have this usual thing, we have written this many times, that the kernel of Pt strictly contained in kernel of Pt square, and this goes on until we reach this point. So yeah, so this is the saturation exponent I should have recalled. This is the saturation exponent of the eigenpolynomial P. This is the largest non-negative integer such that this thing divides the minimal polynomial of T. So that's this notation. I'm just recalling. Okay, so these are strict containments, and we have reasoned this out many times as to why this is the case. So let me not repeat that. So all we do is we just pick some vector in the set difference set difference of the ultimate and the penultimate. Okay, because of strict containments, this is a proper subset of that guy, and hence there is such a vector v. So we just pick one, and it is easy to see that the smallest non-negative integer k such that this is 0 is same as the saturation exponent. That's immediate from the choice of the vector v. Okay, and therefore by what we recalled? Therefore the cyclic degree of the vector v is same as this is the smallest integer times the degree of the eigenpolynomial, which is same as the degree of this thing. So that proves our lemma. Okay, so that's a very simple lemma. And now for the main event. Fix an endomorphism on a vector space V, and we want to show that there is a vector V such that its cyclic degree is the maximum possible. It is equal to the degree of the minimal polynomial of T. Okay? So let's get started. So we will develop some notation. I mean, we are not developing any new notation. We are just kind of recalling the things. So what have I written? Let me make that precise. So this thing here is, this is the set of all the eigenpolynomials of T. So that's a notation. And this thing over here is the saturation exponent of P. Okay. All right. And we know by primary decomposition theorem that the vector space is the direct sum right? And another notation that we will develop here, that thing is what we will call VP. Convenient notation, that's all. Okay, so far we haven't done anything. So now let, by the previous lemma, let little vp be chosen in capital VP such that the cyclic degree of VP is the maximum possible amongst all members of VP. That is, it is degree of, sorry, what am I writing? Degree of px to the power psi p. Okay, this is by the previous lemma. We can do this and define V as the sum of all of these VPs. Okay, and we will show that the cyclic degree of V is same as the degree of the minimal polynomial of T. Okay, and that will finish our proof. So let's get going. So let fx be the smallest degree monic such that the corresponding endomorphism kills V. Right? And by something I perhaps should have recalled, we just know that the cyclic degree of V is the degree of fx. Okay. And by this, by the star mark problem, we also know that, so what do I want to say here? So then fx divides the minimal polynomial, right? This is by the star mark problem. Okay. So say, or let me write it below here, say fx is like that. Since this divides that, and this mx is same as mtx, maybe I confused you. This is mtx, the minimal polynomial of t. So since fx divides mtx, fx has to look like this, where each kp is at most psi p. The reason is that px is irreducible for each eigenpolynomial. Each eigenpolynomial is irreducible. So if fx divides this guy, meaning it divides this guy, then fx should look like this, where each kp is at most psi p. So we record that. Yeah. And what we really want to show that kp is actually equal to psi p for all p. That will finish the proof. Right? Because if we are able to show that, then fx would be same as the minimal polynomial. And hence the cyclic degree of v would be same as the degree of the minimal polynomial. This is what we want to do. Okay. So suppose not. Then there is some q in this some eigenpolynomial for which the corresponding thing is strictly less than the corresponding saturation exponent. Okay? Alright. So now since this is 0, we have in particular, this is an immediate implication of the previous equation. We can add things, we can put whatever we want here. So what we will put here is everything except the eigenpolynomial q. This whole thing will also kill v. Why is that? If this is 0, then this is clearly 0. These two things commute, so you slide ft to this side and then kill v. So this is just a very simple implication. And yeah, so here is what you should note. Note that this thing which is here, this thing applied to v is same as this whole thing applied to vq. So why is that? Well, you write v as the sum of all these things, and vp will be killed by this guy as long as p is different from q, right? Because the killer is already sitting here. For each p different from q, the killer of vp is sitting here, so that will kill it out, right? So the only thing that survives is vq, and therefore this is equal to that. Okay, so by this observation and by this equation, we get that this is 0. And yeah, so we will make some changes here. Yeah, so let's write down the expression for ft that we had, or the expression for fx that we had, and we will also multiply it with something extra. So I will explain. Okay, so maybe I'm confusing this a little bit. So let me just write the expression for ft. Expression for ft is this. And the rest of the term is this. That applied to vq is 0, that we know. But let me write this thing in a slightly different way. So we kind of extract out the term corresponding to Q. So that product is, and this was not Psi P, this was KP. I'm sorry about that. So I made a mistake in my exposition. Sorry about that. Yeah, so what was fx? Fx was this product px to the power kp, right? So all we did was we were writing it as a product of all the things which are different from q. And here is a kp. I wrote psi p by mistake. It's a kp. And here you have a kq. Even if you write a psi p here, this equation would be wrong, but that is not what I wanted to say. Okay, so all we've done is just substitute the Gori expression of ft. And that gives us that this is 0. We haven't done anything, just combine these two things. Okay, and let us call this whole Gori thing as qx. So this is what we will write as capital Q T. So what I mean is qx is this product px to the power psi p plus kp. Therefore qt is that expression. So instead of writing this one line extra, I have just written it in line. Okay, and here is what is important to note. So therefore the GCD of qx, I mean capital Qx, and this thing, what do I really want to use? What I really want, so this GCD is 1, this is 1, and hence in particular this is also 1. So why is that GCD 1? Well, all the reducible factors of qx are the px's, where p is different from q. So the relative primality of capital Qx with little qx is clear, and that implies this, because qx is an irreducible polynomial. Or maybe you don't even need irreducibility, but anyway, so it implies that. So, okay, we have that. And this equation also reads, just by change of notation, it just reads that this is 0. Okay. Now by Euclid's theorem, we know there exist polynomials ax and bx for the base field such that ax times that plus bx times capital Qx is 1. We're exploiting this thing and using Euclid's theorem. And this implies at qt psi q minus kq vq plus, immediately we get that. And now we multiply both sides by an appropriate thing, and that appropriate thing is qt to the power kq. Right? We can do that. So this gives us that, and the two terms on the left side are both 0. So this thing is 0 because each generalized polyeigenvector corresponding to the eigenpolynomial q will die when you apply this. So this is 0, and this is 0 because we showed it earlier. This is 0 as written over here. So those two terms are 0. and therefore this is also 0. Right? This is also 0. But therefore we must have that kq is at least the saturation exponent. Because how was VQ chosen? VQ was chosen so that the smallest integer here which kills this is same as the saturation exponent. So in fact, we show that KQ is equal to psi q. It cannot be greater than psi q. So we have this. And this is a contradiction because we assumed that KQ is less than psi q. So this contradiction proves our desired result. Okay. So that's the proof of the optimality or the existence of an optimal vector in some sense, optimal in the sense of cyclic degree. But if you analyze this proof carefully, you will find that we have proved something a little bit more. We've proved that if T is an endomorphism, Mx is the minimal polynomial of T, and this is the collection of all the eigenpolynomials of T, and we have a vector V which we split using the primary decomposition, we split it. Then the cyclic subspace generated by V is the direct sum of the cyclic subspaces generated by individual components. And the cyclic degree of V is the sum of cyclic degrees of the individual ones. Okay. So, I mean, if you just work that proof out, you will see this, and this implies the previous thing. I mean, this is a generalization. This is what we really did. All right. So yeah, with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.